Good morning, everybody, and welcome to this second training event of Sharework project that will be dedicated to the human factor that intervene in human-robot collaboration. I am Simona Neri, and I am the project coordinator. Okay, just a brief overview of the agenda of today. We will have just a brief welcome and overview of the project. Then we will move to 4 different lectures that will last among 25 minutes. We will have the first 2 that will be given by Paul Eichler and Dionysis Andronas. And then we will go for a brief coffee break. And then we will move to the last second 2 lectures given by Alexandra Jonet and Dionysis Andronas. At the end of the session, we will have a dedicated timing for question and answer. So I kindly ask you to put all your questions in the dedicated tab in the GoToMeeting tool. And regarding the rules, after each presentation, you will have a brief self-assessment questionnaire. This is done in order to keep you awake during the presentation. And at the end of all the presentation and during the next few days, you will get also a questionnaire and a survey dedicated to the quality of this training. So I kindly ask you to please reply to it. For us, it will be really useful. So the speakers of today, myself, Simona Neri, the project coordinator, then Paul Eichler, head of the group Human Machine Interaction at Fraunhofer IWU, Dionysis Andronas, that is a research engineer from Laboratory for Manufacturing System and Automation, and Alessandra Junet, European project manager from Strain Innovation. So just the brief overview of the project. Sharework project is a 4-year project that received 7.3 million fundings, and it is composed of 15 partners coming from 6 different countries. What is the need and the idea behind the project? Currently, there are about 2 million robots in the world, but just 5,000 units are used for collaborative tasks among human and robots. Thanks to the move of Industry 4.0 and 5.0, there is an increase of the market that is expected to reach 3.7 million by 2023, so really soon. Which are the main objectives of the project? First of all, to design the knowledge base and the semantic environment. This was done at the beginning of the project. And then develop a human-aware dynamic task planning and robot offline and real-time motion planner. Then to develop a multimodal human-robot communication system and to find methods that allow us to overcome all the barriers that are related to the humans and their acceptance. The solutions that are developed in Sharework project are mainly divided in 4 different areas. The first one is perception. Thanks to the use of sensor, the system are capable of monitor both the environment and the presence of the humans. The second area is dedicated to the motion planning. So the system are able to identify and recognize the tasks that are performed in the industrial plants. And in this way, we are developing modules that are able to schedule human-robot collaborative tasks and are also able to create a motion planning of the robots that is safe. We have also different modules that are dedicated to safety and security. Here we can list one dedicated especially to the human safety in the industrial plants. Then we have one dedicated to data security, the evaluation of the ergonomics, and some trainings thanks to augmented reality. And finally, everything can be possible just thanks to a human communication module that is able to make possible interaction among robots and humans. And finally, the human factor that this training is dedicated to today. Our industrial cases are listed here. We have one in the railway sector, in which the industrial partner is Alstom. Then we have one dedicated to the metal sector, Cembre from Italy. One in the capital goods market, Goitsper in the Basque Country. And finally, in the automotive one, we have SEAT. The project is divided in 4 different phases, and currently we are almost at the end of the project. Indeed, we are finalizing it in October, and you are all invited to our final event in Barcelona. And here we are performing the integration, the validation, and the evaluation of the industrial environment. Currently, our prototypes are already moving to the industrial plants, and we are currently validating them in the real industrial environment. So here you have a brief video of the project. I hope you will enjoy it, and also our training session.
In the age of Industry 4.0, the industrial landscape is being transformed by technologies, allowing factories to be more connected and automated. Industrial robots have evolved considerably during the past decades, improving in productivity, efficiency, and security. But they are still not flexible enough to coexist and share production tasks with humans. The EU-funded project Sharework aims to provide robots with the necessary intelligence to safely work with humans without the need of protective barriers. Thanks to Sharework, industrial collaborative robots will be capable of understanding the environment and human behavior. A solution to boost process productivity and improve workers' well-being with better ergonomics and safety at the workplace. The resulting technology will be validated in the assembly areas of 4 different companies of the automotive, railway, metal, and capital goods manufacturing industries to evaluate its applicability in different industrial processes. A new smart robotics system for fostering industrial competitiveness in Europe. To find out more about Sharework, visit sharework-project.eu or find us on Twitter.
Okay, so let's start our training courses. We have our first speaker, Paul Eichler. He is a medical engineer from TUC in Germany. He has been researching as assistant in robotics in different R&D and innovation projects since 2021. He is the head of the group of human-machine interaction within the Department of Cognitive Human-Machine System in Fraunhofer IWU, and today is going to give us a lecture about the challenges and the potential solution for the ergonomic evaluation in agile human-robot production systems. So thanks a lot, Paul, for coming today, and I give you the floor.
Thanks a lot, Simona, for the short introduction, and it's a great pleasure for me to be here today. I'd like to welcome you too here to the training session. The next 20 minutes will be about challenges and approaches for ergonomics evaluation in agile human robot production systems. Yeah, the next 20 minutes I will give you an overview about general ergonomics principles, some requirements and concepts, especially for new ergonomic assessment approaches. This information and knowledge is presented on the basis of the development of the Sharework process module number 13. And since this is a training session, I will, after starting with some motivation for the development, I'm going to explain you some basics, and then we will proceed to dive into the activities that were done in the project, and I will show you the main achievements and end with a conclusion and outlook. So let's start with motivation and some ergonomics basics for all of you. Yeah, we can check the project proposal, and the following motivation is presented there. Namely that Sharework will watch for the human's welfare, performing a continuous evaluation of human ergonomics and taking into account human factors within the development phase. So, and to understand, in order to understand the underlying motivation, we should take a look at the current and in particular the future design of industrial production. And as you all may be aware of, we are facing shorter product life cycles in combination with mass individualization. And yeah, this is why industry and research institutions are developing technologies for more flexible production systems. And even in times of Industry 4.0 and smart automation solutions, man with its manpower and abilities as a highly flexible player plays a key role in such factories. And especially in these factories, man will work, of course, side by side with smart intelligent robots, both forming a highly efficient symbiosis. This trend not only affects on the production technologies, but of course also on the operators and their ergonomics. And conventional and widespread way to conduct such ergonomic assessments is to use so-called pen and paper methods. And in most of these methods, the calculation of point values makes it possible to estimate the probability of health damage. Yeah, a known limitation of using such manual pen and paper methods is the risk of low accuracy, high intra and inter-observer variability. And when we think about the HR production of the future, the applicability of such ergonomics evaluation using conventional, so offline pen and paper methods is of course limited. So we can conclude that such offline strategies are not designed for short-term changes in production processes, which we will but have in the future. So, but let's ask the question: what is ergonomics at all? For many people, the word ergonomics is associated with comfy office chairs, the correct height of computer screens, computer mice, consumer products that have been sometimes randomly labeled ergonomic, like kitchenware, backpacks, and gardening tools. But the word itself, it comes from the Greek words ergon, which means something like work, and nomos, which stands for laws, and it can be roughly translated to the science of work, focusing on human activity. Definition is shown here. So let's take a brief look at the benefits of good ergonomics. Good ergonomics not only guarantees well-being of the operators, that's more or less clear, I think. Furthermore, it leads to reduction of work absenteeism caused by work-related disorders or physical or mental diseases. As you can see in this overview, ergonomics is not only has not only impact on the well-being and health of employees, whether good ergonomics has really positive influence on numerous economic criteria. So, for example, it can lead to improved product quality and productivity. For this reason, companies should not underestimate the positive aspects of good ergonomics. So ergonomics is far more than just heavy engineering and has a lot of economic value it can bring. As you probably know, we can distinguish between physical and mental stress. In the following process, we will only focus on physical stress or load in the next slide and also in the scope of Sharework. And what you can see here is the so-called stress-strain concept proposed by Wormwood. It describes a stress is exclusively about objective variables and factors acting on the human being from the outside, whereby the effect on the human being is not considered. So employing the stress-strain concept ensures that the ergonomic assessment, meaning the measuring and evaluating of human labor, respects people's individuality. So according to the stress-strain concept, it cannot be determined only by considering stress. Stress is dependent on the individual characteristics, abilities, skills, and needs of the certain worker. So always keep this in mind, because the practical evaluation methods take into account standardized human models and meet the individual characteristics of persons only to a limited extent. So please keep this in mind. We also always have to consider the individual human. So maybe let's see what long-term effects can occur when people are under or overloaded. So you may also be already aware of the problem that there is not only the danger of overloading the body, there's also the underloading, which can also lead to unwanted consequences in the long term. So in general, we can distinguish between positive or negative stress. And this is valid for mental or physical stress. In an upcoming slides, we will also only focus on physical stress, but just for your knowledge, there's of course also mental stress, which we can evaluate and optimize. So when we talk about negative stress, it is also defined as so-called de-stress, and the consequences are more or less clear. I think, especially the performance can be limited, and it can lead to diseases or the inability to work. On the other hand, we have also positive stress. So this should also be a learning for you that, of course, stress can also have positive consequences on your health and well-being, or the health and well-being of workers. So it can, of course, improve your training condition, your performance, and help to improve your skills and abilities. So there's also always a trade-off between the amount of stress and not reducing the stress to zero in the workplace design. So let's get a little bit more specific and look at one of the main risk factors for physical stress, namely posture or postural loading. There we can distinguish between good posture, which is a position where the functional structures of the body are in the best possible position to exert high forces or high precision movements. And indications of good postures are balance, symmetrical distribution of forces on the body parts, and skeletal loading rather than muscular loading. And then we have, on the other hand, bad posture, which is a position where the body is in a weak position to perform its physical demanding work. And it of course puts additional and unnecessary stress on the body tissues and does not contribute at all to the accomplishing of the given task. Indicators of such bad body postures include positions at the outer range of movement, so for example hyperflexion or hyperextension, asymmetry or imbalance between the legs, and forced muscular loading. All right, now that we have looked at some basics, let's identify some more specific needs for innovative ergonomic tools. So on the left, we see the continuing trend of increasing product variance with decreasing lot size, which is facing us more and more already now. And we can expect that digital tools for ergonomics can help us in coping with increased complexity. This is shown on the left side. And of course, appropriate digital tools can lead to cost savings through early concept validation and continuous evaluation of ergonomics, which is shown here on the right side. Okay, so let's check this brief overview about simulation software and motion tracking tools that may help us in mastering ergonomics. For objective human motion data, we can use, or for gathering objective human motion data, we can use so-called marker-based systems where we always need to put on special markers in the subject. So always we have to put on these markers on the human to gather our data or have motion capturing. On the other hand, we have for the estimation of motion behavior simulation tools, which means rather high effort in modeling the processes in most cases, and the simulation covers with high probability only limited the actual behavior of your employee. So it is using predefined human models that have some constraints are not really one-to-one showing the reality. So this leads us to the conclusion that we, or Sharework, wanted to develop an ergonomic assessment tool that works without sensors on the body, so it's highly flexible, and which is based on markerless motion capturing, which is indicated here, different solutions to do this, to track the human without any marks. So we know now that digital tools may help us in coping with the complexity of agile or flexible, highly often changing production environments. But let's look how ergonomics evaluation is usually done and find solutions how to adapt or further develop new approaches. The conventional way to conduct such ergonomic assessments is to use, as already said in the beginning, so-called pen and paper-based assessment methods. Some of those are shown here in the overview. And most of these methods, the calculation of point values makes it possible to estimate the probability of health damage. One of the most comprehensive and widely used ergonomic evaluation methods is the so-called ergonomic assessment worksheet, EAWS, shown here, which is a worldwide standard for the development of safe working methods in ergonomic risk assessment. Yeah, so we have an overview here. We have the limitations of pen and paper methods and are now looking for new ways to fulfill our requirements of highly variable production processes and also the individuality of each person or each worker. So we come to the following hypothesis and the scope of Sharework's module number 13. And the hypothesis is that online ergonomics assessment and real-time feedback ensures that the employees improve the quality of their work and maintain healthy working conditions, which is, of course, based on the Sharework motivation, which is described above. So our solution is that we propose a method that is marvelous, and so with other words, camera-based, and is using real-time joint position estimations as input, and calculates ergonomic criterion and evaluation, and provides then continuous and summarized individual ergonomic feedback to our worker or the guy who is responsible to optimize the processes. So this brings us to the overall purpose of the Sharework module. The purpose is declared here. So we want to evaluate and optimize workers' ergonomics in real time. So we have to in real time check the situation, and we have divided this module that we developed in for two main processes or reasons. First hand, the short-term online posture feedback, which really works in real time. And then, of course, we also have the long-term analyzing functionality that we have a long-term ergonomics or shift reporting. Yep. So let's check the activities that were performed and look into the main achievements which were performed during the project. Overall, or in general, the constraints were, of course, predefined by Sharework's overall system architecture, which you maybe have seen also already before. The scope of the modules was predefined, and the communication interfaces were coordinated during the project. To achieve the system modularity, we wanted to achieve the system architecture has been implemented with robot operating system WOS on Linux and was melodic. This figure here shows the architecture and communication structure between the different modules that are involved here in the ergonomics assessment. You can see it here. So we are focusing in the upcoming minutes on this module here, which communicates with the other partner modules. Yeah, and of course, in the beginning of our development, we have identified key requirements for the module, and in the context of the overall system. Those are shown here. Some examples. So one of the main requirements is, of course, the local flexibility we wanted to achieve. So the system should be highly spatial flexible, so we can put it on somewhere on the factory floor and just evaluate or evaluate the ergonomics situation. And of course, it should be easy to use, and usability should be addressed. And yeah, the way to set it up and use it should be really, really short and efficient. Yeah, this brings us to the one main function that the overall system, of course, has to bring with it. This means the model-less tracking. So at the beginning, we did a research on market available sensors, algorithms, and middleware, which can give us 3D skeleton information based on 3D camera information. And this figure here shows us some market available products and its specifications. For the pre-implementation, so really meaning only in this module, we used so-called NuiTrick SDK middleware to track humans or have a pre-implementation that allows us to have a preliminary data acquisition and processing pipeline. So we set up this pipeline, and this allowed us to have some reference data input stream for our ergonomics assessment module, so namely the module number 13. But of course, this is just a simplified test setup that was used for initial testings and validation. At the end, in Sharework, we have a more complex solution, which was done in module number 3, which provides us with real-time skeleton data based on numerous, so multiple cameras, and allows us, of course, to have higher robustness there and higher flexibility. Yeah, but this lies out of the scope of module number 13, so the details for this tracking can be found in Sharework's module number 3 description. So we have our input information from multi-camera human tracking, as showed the previous slide, coming from Sharework's module number 3. And now for the evaluation of the ergonomics and also for the feedback to the worker, we have oriented ourselves to the widely used traffic light module, which represents a three-zone evaluation system, which is shown here. So the traffic light logic can be used to indicate risks in a pretty easy to use and easy to understand way. It's also described in harmonized standards. This evaluation system, three-zone evaluation system, is also already used in simulation environments, existing ones, for example, Siemens simulation software products. And as you can see here, there's an example overview, and it can be used, for example, to show the time spent per work cycle in each posture range. And yeah, this methodology can, of course, help you to indicate which joints are frequently and heavily loaded while the process. So for the evaluation of postures, we have chosen to use a methodology from the German social accident insurance, which is based on so-called scope bands or risk levels, which are also referencing the three-zone model. And yeah, this method allows us to use these scope bands, which are based on articulation angle analysis, and yeah, helps us to analyze certain extremities based on their angles. Yeah, this is this is one of the methodologies we were able to use or we implemented, and this is how you can use it or statistically show the results just in sample example. So we can of course use these methodologies or outputs to also visualize or statistically analyze the movements over time, for example, via pie charts or such graphs here. So the question was also, after implementing these methodologies, how to present information in real time to the worker and not keep it to keep it more or less simple and also applicable and usable for the human. So we, together with the partners, we had to find a trade-off between complex information and usability. And yeah, we have agreed to keep the online feedback pretty simple, to not distract the worker too much, and yeah, to have for each joint such an online feedback via visual information. Yeah, I think some examples will be shown in the upcoming training sections by the colleagues that were dealing with the human feedback module. So this functionality was implemented. So we have this posture assessment via a three-zone evaluation system for each time frame. So we can theoretically, for each time frame of our data input stream, calculate and assess the posture, but in practical you would use a certain amount of time and then calculate the mean, for example. So in addition, we decided to implement features for a more comprehensive ergonomics assessment. So this was the first one I've just shown you, but here we also decided to implement additional features, and namely via EAWS. So these ergonomics assessment worksheet, which is a widely used assessment methods, especially or particularly in the automotive sector. So we implemented parts of EAWS, namely the body posture assessment, which represents section 1 of this assessment technology methodology. So the EAWS itself contains many sections, but we just focused on the body postures in this case for the beginning. You can see here the postural assessment criterions for this assessment in these figures, and this was implemented in the project, and you can see here some of the results. So we achieved the following was implementation overall. So we have joint 3D coordinates coming from our motion tracking from the module number 3 as inputs, and we can assess this real-time ergonomics postural criterions live in real time or over time, and output or give feedback information to the worker or anybody who is interested in this ergonomics assessment results. So a strongly simplified version is presented here on the figure, as you can see. And I also have a video here which shows the real-time capability of the module, which was just done using the pre-implementation, so the one camera version, which was not the final one as already said. And here you can see that all the extremities are assessed, and postures and also the angular ranges are calculated and can be put or can be streamed to the human or whoever. So so you may have noticed that the simplified tracking in the previous version was only simplified. This video presented the single camera prototype, which was only used for the pre-implementation testing. So as already said, in a separate module number 3, a multi-camera system has been implemented in Sharework to realize stable 360-degree human tracking. And this, of course, improves the spatial tracking capabilities and robustness against object occlusion. You can see here the compatibility to different skeleton models, which we could achieve in our project. So the final communication structure between the involved Sharework modules looks as follows here on the slide. We can theoretically capture multiple persons in parallel, and the skeleton data for each person is published and can be used by module number 13, which I just presented. And this module, which we're talking about here, is calculating the ergonomics evaluation, and the results are used by module number 9, which we'll also see later on, presented by a colleague. And this can of course be used for worker feedback and long-term ergonomics reporting. That brings me to the conclusion and outlook. Overall, Sharework follows a modular system approach, which you might also have seen before. This is allowed belong others by using the WAS operating system and using different nodes, which can be seen as modules that communicate via publishers and subscriber logic between each other. In this case, our module number 13 is the node that is exchanging data with module number 3 and 9, and via additional WAS services can also configure the assessment module And yeah, of course, we can use this information, as already said, for output to the worker or online feedback. And concerning the worker feedback module, the user can receive at the moment feedback information consisting of the settings and a color flag for assess joint angles based on this traffic light system, information about the posture types, and of course additional textual information with further details. Detailed information for the user feedback can then be found in the description of the partner module number 9. Yo. Oh. This was just go again. Yeah.
Thanks a lot, Paul, for
conclude the meeting. Sorry, I had the technical problem. For feedback or questions, you can contact me, of course, by email. Yeah. Thanks a lot for your interest, and yeah, looking forward for discussion or questions.
Yes, thanks a lot for the presentation. Yes, I encourage the audience to ask all the questions in the dedicated tab in our GoToMeeting tool. And also to get ready for our questionnaire now, self-assessment questionnaire. So here you have the question. Okay, the 40% of the audience answered already. We will wait for 20 seconds more. Anyone else that want to answer? Okay, here you have the answer of today. They are pretty distributed, so it was not fully clear the answer. Paul, can you help us
Yes, of
on
course.
this question?
I'm just checking out how to see the results because I'm still seeing only my screen.
Okay, so yeah, the 33% replied that only B and C, and then all the other were replied about percent from 10 to 24%. All the other possibilities.
Okay.
Yeah, you were right. The correct one was the D one, but please, Paul.
Yeah, it's more or less a tricky question because, of course, robots influence how we design or also the risk of an application. So when, of course, robots are taking overloads, the loads are not distributed to the human. But to be specific, of course, overall, especially when we talk ergonomics, we consider the human itself. So there, of course, the individuality has an influence on the human, on the ergonomics. That's what I presented at the beginning. So that, for example, we can use this stress-strain concept or model, which also explains the individuality of each person. And in most engineering methods at the moment, we still just use standardized human models, which not really, of course, represent at the end the worker that is actually working there on the shop floor. And number C is also, of course, the exact answer, because this is also the main motivation for this development, which I just presented here, that with the increasing flexibility, of course, we have higher efforts to evaluate and also plan factories, and also with the aspects of ergonomics. So when we have high variance, often frequently changing processes, it of course gets more and more challenging to engineer and assess our workplaces. So the just proposed methodology, which I just showed the last minutes, wanted to have wanted to be one solution or proposal that allows us also to be used in such flexible production systems where we can really online track and assess the human movements and ergonomics. Yeah. So B and C is correct. Robots are taking overloads is also making it challenging, but yeah. Thanks.
Yeah. Okay. So now we'll have also another brief survey. Okay, thanks a lot, Paul, for the lecture, and also to the audience for being proactive and reply to our questions and surveys. And now we will move to our second session. It will be given by Dionysis Andronas, that is a mechanical engineer, got the bachelor and master degree in mechanical engineering and aeronautics in the University of Patras, and now he currently works in the Department of Robots, Automation and Virtual Reality in the manufacturing group of the Manufacturing System and Automation. And he is one of the pillars of Sharework project. So I'm really glad to give him the floor today for this lecture in challenges in work adaptation, the Sharework operator training approach.
Thank you very much for the introduction. I hope everyone can see my screen. Okay, as Simona introduced, I'm going to present you this session. We may now begin with an introduction of the general context. So, recent years, industry focuses on balanced productivity, cost, and also quality and flexibility for satisfying the market requirements. In order to do so, manufacturing systems are shifting from mass production to mass customization, and in order to do so, they are using Industry 4.0 and ICT services in order to make their systems capable of adapting more easily to dynamic production changes. Now, this creates a number of challenges, and workers need to deal with manufacturing of multiple products during the shift, regarding the introduction of new manufacturing or assembly routines per new product, and of course they have to handle the complexity of modern working environments. The last one actually involves working with sophisticated tools of machinery, cooperative robots, or even mobile manipulators. Also involves following specific process plans and as well as following execution and monitoring procedures. And this is important because if they are not able to do so, this could lead to potential system stop. It could lead to loss of data because if they do not follow the monitoring procedures, then businesses will not have reliable data in order to use them for other analytics and also. It could lead to quality issues, fluctuations in key performance indicators, and most importantly, it could lead to safety risks. And what about operator training? Despite the complexity that the modern manufacturing systems present, the training procedures are limited to traditional means that involve operation manuals, seminars, workshops, etc. In parallel, all this immense growth of the Industry 4.0 and also the harsh and competitive environment that stresses the businesses to recurrent changes does not allow them to develop and establish modern training schemes in advance. However, we could exploit the advances in technology, and we should deliver pioneer training frameworks that will ensure, of course, high operator interest and well-being during the training procedure. And this, of course, will lead to steeper learning curves and shorter training periods. And also, it will provide better tools in order to familiarize operators with the cyber-physical systems of the IoT era. Training is a topic that has gained a lot of interest, mostly from academia, and the previous studies have focused on providing the technologies for increasing the attractiveness and also the performance of the training sessions. They have done this by using technologies like virtual reality, simulation, and also augmented reality. If we compare those three technologies, since augmented reality overlays digital content on the operator's field of view, related training sessions can take place even within the physical workspace that will be used during runtime. So operators could have a head start at the workstation and be more prepared for the real operation circumstances. In the same vein, of course, we can develop training of the job approaches where operators are also trained during the actual runtime. Now, some studies also have indicated that if we compare those three technologies, the augmented reality can surpass in aspects of efficiency and performance conventional screen-based applications. Okay, so based on this, what we're doing in Sharework? In Sharework, LMS has worked on the design and development of a novel operator training framework that is based on augmented reality. We have developed a number of applications that support multiple modalities that are important for interacting and controlling the system in order to familiarize, of course, operators with hybrid systems based on human-robot collaboration, and of course, IoT technologies and new assembly operations as we described in the challenges. At first, we could have, for those who are not fully aware what augmented reality is, through the years there have been a number of terms about AR. Some of them are here in this slide. Augmented reality can be described as a way to augment the real world with digital and virtual objects. Or it can be described as a way to combine real and virtual objects in a real environment that can run interactively and also in real times, that are geometrically also aligned. And those terms are also visualized through those indicative figures. The left one is from the operator's point of view, where we can see that the operator is able to have in the physical workspace a digital cube that serve a specific purpose for this process. And on the right side, we have a more illustrated way of how operators are interacting with digital items in their workspace. Now, the developed training module facilitates operators that are both amateur or even experienced with two main aspects. At first, we have the Industry 4.0 workstation, and on the second, and on the other hand, we want to familiarize them with the frequent product and assembly procedure updates. Subsequently, we have two distinct training modes. We have the training mode that is responsible for introducing operators into the functionalities of their working areas and also the events that they are going to encounter. And on the other hand, we have the assisted modes that through augmented items, models, and panels will introduce the operators into the new assembly routine. During the design process, we want to make the applications more usable and more intuitive, so a user-centered design method was used, and that means that we consider in a closed loop comments from the users and make them our design requirements until we reach them and make them all specification. In parallel, something that is also indicated in state of the art, we want to follow a gamification approach during the procedure in order to make the training experience better and keep the interest levels of the users higher. Okay, so we may now proceed on describing each training mode more specifically. The first one is actually offers a walkthrough session where all the functionalities of the HMIs and also the resources are analyzed sequentially. So the operator can walk inside the workstation and interact with digital items that describe the available resources and also their controls. And on the other hand, the operator is also introduced on potential production events. For example, what could happen during a safety or security incident, or also how information from monitoring modules could be presented to the operator during runtime. And for example, on this figure, we see how the operators are introduced to the ergonomics feedback from the module that Paul has already described to us. We move now to the second mode, which is the assisted mode. As explained, it focuses on describing assembly operations and how those should be properly executed. In this mode, the users can interact with digital models, move them, rotate them, and explore critical aspects for their joint processes. And this is also supported by relative workpiece movements or even arrows. Now, in the same mode, we have established an additional functionality, which is called, of course, physical object detection. And this one actually uses the integrated camera on the HoloLens headset that we are using and is able to identify the object of interest. So if we are discussing for a specific assembly procedure for an item, if this item is inside the working area of the operator, it is highlighted through an augmented item. More specifically now about this object detection, it is based on parallel machine learning approach. We selected this method because it offers quite reliable results in high frequencies. And this is important because as the operator moves around, the sensor receives different images in quite high rates. So we wanted the method to be fast as possible. And as happens with methods of this type, we created the data set of positive and negative images containing thousands of pictures of the objects of interest or not. We trained the model, and then we ended up with a cascade object detector. We can now see some video presentation of how those modes are working. So at first the operator selects the modes. Now we are seeing the training mode. At first the operator is introduced on options panels that an HMI that we have developed in Sharework contains. So before actually using this HMI, the operator in runtime, the operator will be aware of how to customize it. The operator is also introduced on monitoring feedback that is going to receive. Here we see the ergonomics feedback, how this will be provided. We'll move on a little bit. We have also available video assistance if needed, and then we have also robot related information. In parallel, the augmented models for assembly support are also described in combination also with textual instructions and so forth. In case of data security incidents, that will also mean that the system will freeze. The operator is introduced on how to respond. Here we see an augmented robot and how robot trajectories are going to be visualized in real time. This is important because if the operator encounters a robot trajectory without being informed about it, it will not be so useful information. And this is how the first mode ends. We move on now to the assistive mode, which is related about the assembly operation. We see how the user is able to interact with digital items. The assembly routines are visualized, and also the components of interest are highlighted by the object detection module. I move on a little bit. We have arrows that indicate, for example, where screws should be placed. And this operation is repeated for all the assembly steps. We see how the second object is recognized, and also how a third object is also able to recognize for the related assembly operation. We move on now to a second prototype of our module. Here, this prototype is oriented on the shared assembly use case. So for the training mode, the operator is able to interact and learn all the functionalities again of the same HMI and what kind of information is going to be streamed. For example, we have the textual task information. We have a description about all the available holograms that are going to be presented and what they actually mean. We have also video representation. For this prototype, we also tested if video representation, for example, of the trajectory, not the actual trajectory, will be better to comprehend what will appear during runtime. Description about the safety zones, security incidents, and this is how this training session is completed. We move on now to the second mode. Here we tested a different approach. If the operator is able to navigate through the physical workspace, we can see an augmented robot to simulate what will happen during the actual runtime. Then we have augmented markers that indicate where the operator should go for performing an assembly operation. We have videos that instruct the user of how to perform, for example, in this case, manual guidance operation with the robot. We have augmented items on where to put screws for securing the assembly. What actions are needed, for example, to close the door after the assembly, and the same process is repeated for the second door. Here we see the robot to manipulate in augmented format in the physical workstation the product. And the same process more or less is repeated. Okay, and now we may move on to the results and conclusions we have from this work so far. The first application prototype was tested through a series of experiments where we have subjects from originally from two experience groups. The first group was aware about the assembly process of the product, but they were unexperienced on how collaborative systems work. They haven't been near human-robot collaboration demonstrator of physical cell. And then we have the second team, which is exactly the opposite, where they have been where they have interacted in the past with a collaborative system, but they are not aware about the assembly process of the product. After merging all those the results of questionnaires based on the system usability scale, we reached an overall score of 82%. Now, if we focus on comments that they gave us after the experimentation, they expressed that both training modes were very intuitive and they were easy to use. The operators were able to use the system without needing any advanced skills, and they thought that they are feeling that they can get familiarized with collaborative systems quite more easily than actually going directly during runtime or having traditional means of assembly like manuals. In parallel, the training in the physical environment using augmented reality items avoid cognitive workload, and I can describe later what this actually means. And also a comment that I would like to add here that is based on our earlier prototypes, where of course the object detection motion was not so major. When the dataset was not so reliable, we had a lot of false positives. So the field of view of the operator was filled with random square blocks that indicated objects that they were not there. This was very confusing, so as a functionality didn't work well at the beginning. But currently, through a reliable dataset, we can say that it's at the point that it facilitates operator and makes them more confident about the operation rather and not actually blocks the training procedure. In overall, the proposed training module proves that AR can enhance the training practices that are used in industry and achieve steeper learning curves and also faster operator adaptation. The augmentation now of the physical world, instead of navigating to a virtual environment or simulation, limits the cognitive workload. This is because the information of interest, what is actually important for each training step, is visualized through digital items that stand out inside the operator's point of view, and the rest of the scene is perceived through the physical world. So it is easy to follow up the assembly operation. It is easy to follow up the instructions that are provided, and the operators are not confused on what is the feature that they have to pay attention to. As mentioned, those frameworks can be valuable for businesses, and it is expected that if such training frameworks are implemented, the users can be adapted more rapidly to production system changes and keep up with modern market requirements. Thank you very much for your attentions, and I'm looking forward to questions at the end of our training workshop.
Thanks, Dionysis, for the clear presentation. I think that this kind of demo help us to understand better how to put in practice the technology that you are developing. Yes, again, please put the question in the tab, and here you have our quick questionnaire. What will be more difficult for you to adapt? Recurrent workstation changes, recurrent assembly sequence and product variant changes, IoT technologies and state-of-the-art on HMIs, fenceless coexistence with robot. You have 30 seconds more.
There is no correct answer. This is just as a feedback from the audience in order to see what is actually the biggest need for the training sessions.
And what's your opinion, Dionysus, here?
Personally, I would think that interaction with ICT technology and also the fenceless coexistence would be the most trickier, because robots more or less currently are expressionless, so the synchronization of tasks and also awareness about their actions is the trickiest part so far, based on my experience and point of view.
Okay, here you have the answers. The 30% of the audience gave the answer B and D. So recurrent assembly sequence and product variant changes and fenceless coexistence with robot. And then also the remaining part is divided into two in A and C. So here you have the opinion of our attendees. And now we have also a quick survey. We take 30 seconds. And then we will be able to move to our coffee break, a really quick coffee break. We are just a bit late, but you will have the possibility to have at least one espresso. A few seconds more, and then we will close the survey. So I think that since we are just a bit late, we will be back at 11:15 for the other two courses we will have today. So see you in a while. Welcome back to our session. So now we will move to the next presentation, and I'm really glad to introduce Alexandra Junet from Strain Innovation. Hi, Alexandra. I cannot hear you. In the meanwhile, Alexandra joined Strain in 2020 as a project manager and also a Sharework project. She is graduated in political science, and she is currently working in planning and facilitating workshop, webinars, and sustainable resources management. And she is involved in different projects, mainly in the areas of circular economy and collaborative robotics, as here in Sharework. And today she is going to present us a lecture dedicated to the creating the condition of a successful social dialogue to implement collaborative robotics. Alexandra, the floor is yours.
Yeah, thank you, Simona. I welcome you everyone to this session, as Simona said, on the social dialogue in collaborative robotics, that mainly based on the experience that we have from Sharework. I think you can all see my screen, so I will start. So we'll have 4 items to go through today. First of all, the question of trust in human-robot interaction. All the notion of acceptance and acceptability that are key, of course, to facilitate integration of innovation in anywhere, basically. A third item on user experience, how we measure it, what is it used for, and fourth topic on collective intelligence and why it's important to create the condition for everyone to express themselves during such integration project. So a quick introduction to give you a few idea of the goals of the session, how we build a common set of knowledge within a social community to foster trust and perspective taking. So this is the heart of the Sharework methodology that we went with when we started working on human factors. So we had three goals, which were ensuring collaborative governance, building a common ground with end users, and defining the best practices for innovation integration. So all those three topics will be addressed during the following session. And I will quick remind you the learning objectives of the session, which were understanding the science-based methodology, observation, analysis, and collaborative action that are necessary to optimize the impact of a cobotic solution on end users, understanding and applying collective intelligence methodology to define the best practice for innovation integration, and finally, learning to foster trust and perspective taking within a social community. So the goal of this session is basically to give you key factors of success to make sure that the innovation that you are trying to integrate is done and will be sustainable in the future. So a quick reminder of what human factors are about, because as I guess you all know now, of course, when we integrate a robot in a production chain, the relationship between the operator and the robot is not the only thing that's important. Of course, the user has a psychology, a mindset that is important, a set of motivation that we need to explore to make sure that the interaction is going well. But of course, a lot of other factors are involved in all that concerning the environment. So, for example, the other people, the operators that work with the robot, but the operators working before and after the tasks are concerned need to understand what the robot is doing, how it works. Trust needs to be fostered towards the robots, but as well towards management. So the idea is to make sure that the robot implementation is not something that goes top to bottom, and that the operators is stakeholders in itself in the integration, taking into account, of course, the organization. For example, it's of course easier to integrate robots when robots are already implemented, that people are already working with, and in a trustworthy environments. So the governments to introducing the cobots are of course really important to make sure that everything is done in transparency, to make sure that all these difficulties are addressed quickly, and of course ensuring that worker representatives are involved to avoid creating or adding to social tension that could of course exist in any workplace. So of course all that depends on the culture that is taking place in the company, the values, the context that are different in each use case. And finally, it's important to have the support of the management to make sure that operators are correctly trained, that volunteers are given recognition for their work, and that the management is adapted to any impact that the robot could have on the organization. So my colleagues, Dionysus and Paul, already mentioned a lot about the ergonomics, physical health, and cognitive processes that are taking that are involved in all the organization, task, and workplace. So all this environment is important, and we need to be addressed to make sure that the integration goes on correctly before and the robot is deployed, during, to make sure everything is all right, and after, to make sure that the impact of the robot is actually beneficial to the end user. So that's all those factors that we are trying to address with the all-human factor methodology. So we will start with the question of trust in human-robot interaction. So trust is, of course, key in any organization, and it is especially important when getting involved in non-human assistance, because trust can be defined as the willingness to rely on someone or something in whom someone has confidence to perform an action that is important to the truster, and irrespective of the ability to monitor or control it. So it means that trusting means accepting uncertainty, vulnerability, and control. So all those three needs to be balanced to create trust, and that's why that's what we are trying to create with all the management integration management that really involve everyone because if trust is not created during the integration of an innovation, for example, the operators, ultimately the end user, but of course it can also impact other or its environment, but the end user in particular could feel a reduction of job control, excessive demands, uncertainty increased, the influence he has on his work can be perceived as lowered, his worthlessness he could feel less worthy of working, less useful. And of course, there is this fear of being replaced or being monitored that is deeply associated with robotics. And of course, end user may not be voluntarily users of the developed technology. So what I mean is it's really important to involve from the start the workers to make sure that the technology is not imposed from the top, that everyone understands that it's here to help, and that the working environment is positive and doesn't pressure the workers to adopt the technology, because it will then have a negative impact on the job satisfaction, and of course impact on the motivation and interest of operators in their work. So all those factors have pushed us to create a grounding methodology to optimize this trust, make sure that the human-robot interaction and collaboration is accepted, understood, and for that we had a variety of sources, mainly on social and cognitive sciences. This grounding methodology aims to create mutual knowledge, create a communication and relationship, not only between the robots and the end user, but also between the end user and its management, the management and the robot, that everyone can go around the table and understand what's going on, how we could make it easier, and how make it sure that the robot is integrated and beneficial to the end user. So I put on the right the 7-item scale of trust in technology, which is a work from Sheridan. It's an instrument to measure the efficiency of the human-robot collaboration. And as you see, there is like 3 different items. Some are quantitative, like the statistical reliability, the lack of error that the robot could do, and also the familiarity, the dependence, which is more the perception, in the case of perception of a feeling that is highly dependent of the user profile. So what we conclude from all this is that the key success for human-robot collaboration is understanding and anticipating the robot behavior. Like that's the baseline making sure that the robot is integrated in all this. And of course, it goes by fostering trust and acceptance. So what we did in the Sharework project, for example, is we have 4 use cases that Simona presented quickly at the beginning, and we did the same thing every time. We went there for interviews, field visits to understand the company work culture, the profile of end users, the management methods, make sure that understand how the innovation would be implemented, who would work with it, and basically, sorry, what we did was to, at first, to ask the workers to express their feeling, describing their organization with a few keywords on the task, position, the management, collaboration, culture. So we had these keywords that we could use to better understand how end user perceive their company, and it led us to adapt, of course, our methodology to this culture. So the method is always the same for each case study, but we had to adapt to the variety of needs and profile that we had. So now we will talk about acceptability, because once we foster trust, of course, the idea is to foster acceptability. So because acceptability is not natural, usually humans are mainly distrustful. They prefer to comfort themselves in something they know rather than test something that they are not sure of wanting, being disappointing or dissatisfied. So for that, I put 2 definitions here. So acceptability then is a forward-looking judgment before the use of technology, and acceptance is the judgment after using a technology. So for what we did is, first of all, assess the acceptability of of the workers, to make sure that before even they did their diffusion, we could already identify maybe hot spot that we could address in the design with the technical partners. So I put here 2 acceptability models, of course, to go a bit further in the detail. Basically, we used the unified theory of acceptance and use of technology, UTOT model, to assess the acceptability. So lots of items here related to the performance expectancy, the effort expectancy, sorry, the social influence, and facilitating condition and compatibility. So lots of sub items that are interesting, but one of the two most interesting, in my opinion, would be like social influence, which are the degree to which a user perceive what's that important other believes he should use the system, and facilitating condition, the degree to which an individual feels that an organization and technical infrastructure exists to assist him in using the system. So acceptability depends heavily on the feeling and the perception of the worker, and that's something that we really need to take into account. And so we did. We adapted a version of this questionnaire using specific items to assess the human-robot future collaboration adapted to each use case. And we did those questionnaire using a video of what collaboration would look like with a robot. So workers had a bit a more defined idea of what it would look like, and we were taking their point of view after that. So what the results that we have were actually really encouraging. So because we have, starting from the start of the project, to go on field visit to include them in the process, we didn't have a firm opposition from the operators. Most of them were supportive to the collaborative robots. Of course, among the use case, there is different quite a high dispensary depending on the item, but it allowed us to orient the next step. So as I said, adapted for each use case. what the result that we have were that the workers were identifying the benefits for working condition improvements. They saw the robot as an opportunity for skill development, and they were basically confident in themselves to learn how to use the robot, and they were confident in the means that were provided by their organization as well. However, some concerns were about the abilities to control the robot. So they trust their ability to learn, but after that, just a bit, when we go to interacting with the robot, the concerns are a bit higher. They are concerned as well of the loss of autonomy in their work. So it goes with the fear of being replaced, being monitored as well, because the robots means that everything is more constrained, and basically new set of rules to to do their work. And from that, they have also concern about the way the robot will impact their usual tasks, like how they work, the way it will impact how they work usually, and if it's going to be different. And being different mean learning something new and make more effort at some point to learn something new, and it was a concern. One aspect that is also very interesting is the high level of trust among some operators concerning their ability to control and work with the robots. That could lead then to a possible lack of vigilance and security issues. So even if there is like this huge confidence and trust, that's something that could be seen as only something benefit. We have to be careful and make sure that it doesn't bring some difficulties later. So we evaluated as well the user experience. User experience is the overall experience felt by the user when using an interface and interaction with any device of service, basically. And usability is the degree to which a product can be used by identified users to achieve defined goals with effectiveness, efficiency, and satisfaction in a specified context of use. So those three criteria of usability have been assessed using a method from Jakob Nielsen and an heuristic evaluation so we assessed that to make sure that the operators were perceiving the interest and the efficiency of the robot, that they could bring feedbacks on the design to make sure that it actually fit their needs. And the results of that is, what we did was construct a questionnaire that we combined with the system, based on the system usability scale, and it was 10 questions aiming to determine the level of satisfaction of users of the system. So we did that at the time of COVID. So we had to do that in the same time with the UTOT questionnaire that I was describing earlier. And so we had this video of the cobots, and we asked them to react to the video. So what will be interesting then is, now that we are back on the field, we will be able to bring those questionnaire and do them again and compare the difference between what they felt when they were seeing the collaboration human-robot, and what they are feeling now that they are actually interacting with it. So there is like 6 items: attractiveness, efficiency, perspicuity, dependability, stimulation, and novelty. And all those 3 items make the usability, like it impacts the usability of the robot. Like last item on the menu, I wanted to talk to you about collective intelligence. because the whole process of what we did on Sharework is based on collective intelligence. So collective intelligence is the sum of individual intelligences of member of a team plus their relationship. So it's different from basic collective work because you have the system, so individual intelligence. They all have a relationship with each other that enrich the discussion. So the idea is to have as well a defined group. So with the digitalization, defined group can be open a bit more, but defined group means a group of people interested in the same thing or wanting to resolve one problem. The process is supposed to be evolutive, dynamic, step by step. So usually collective intelligence approach means taking the time to go in depth into a problem and yeah, it's an iterative process of sorts. Of course, the context is important depending on the environment that you work on and the collaboration rules. You have more or less success in creating such a dynamic. But overall, it's a good collective performance indicators because it allows to see if the way to work is something that brings more out of people, of if in the opposite is something that constrains people, meaning that if people feel constrained in the collective interaction, that there is something to change in terms of work and collaboration, that some mechanics are not working properly. So basically, what we did to foster collective intelligence is all that I described earlier, the bottom-up process, combined with experimentation, focus group, having a grounding methodology that creates a common basis for everyone, that everyone is sure about this position in the process, and allowing to to improve the knowledge, mutual knowledge, and make sure that each individual can contribute to the process regardless of their position. So either be it a worker, a manager, a person from a project partner, the idea was to make everyone legitimate about contributing to the process and give end user in particular a sense of ownership of the result. Because that's one of the main difficulty with all these robotic processes. Often it's something technically complex, so it's difficult for workers to understand where it's coming from. And of course they can use it because it's made for them to use it, but it's sometimes difficult to feel legitimate using it and etc. So the collective intelligence process aims to tackle those difficulties from the start. And that's what we did on Sharework. So that's how we did it. So we did, so I didn't put that here, but we did some observation at the beginning of the project. Then we kept in touch with the workers during the pandemic. And then we are starting now the experimentation, observing the operators where they interact with the system for the first time, better understand the acceptability, identify usability issue, and of course, so validate the KPIs. So KPIs for the human factors are the situational awareness, which is the operator safe? Is it aware of its environment and of the robot action? Is it clear for him what's happening? The cognitive load is the second KPI, is how much of an effort is it for him to use the robot? And final KPI is the trust in the system. So as we explained, does he feel confident in using the system? And we saw what were the factors that could improve that. So the experimentation are here to observe. So with a few question and interview, but the main point is to to have a third point of view, a third person point of view on the operators. While the workshop is where we will put together everyone, make sure that the operators can process their feedback to the designer and make sure that we could generate ideas to improve, and also good practices that we could take from Sharework and from this bottom-up approach that we're trying to create. So I will finish with a few take-home messages. So first of all, as I described quickly in the beginning, to develop a safe collaboration between human and robots, there are a few necessary conditions, but the most important ones are the fact that the operators and the robots are able to perceive and predict the other's goals, to understand how it moves, what it's going to do, what's the interaction between the two. And secondly, the building a common ground between all stakeholders. So, and foster communication, basically, because it's really important to make sure that the robot is actually used at the end in a way that benefits operators. Everyone needs to be interviewed. Everyone needs to understand what's going on. And finally, the second thing was to the fact that more often than not, the blocking points to integrate an innovative project in the work environments are not only technological. Most blocking points are actually linked to the human, to the organization, to the task, and to the perception of the innovation by the end user, by the management. So that's essential to integrate a human factor in innovation integration. And yeah, and finally, the final message was that the perception of the collaborative robots and the tasks that can be associated with it mostly depends on the context of use. What I mean is that as the methodologies that are presented can be applied everywhere, you need to adapt all the time to each use case and take the time to understand the variation and the difference that you have, the different profile, the different end users, the different needs and wants from end user, to make sure that the collaborative robot fits precisely the need of the end users. And I think that was all for me. Thank you everyone for listening, and I'm looking forward to your question at the end of the session.
Thanks a lot, Alexandra, for this complimentary talk. I think that sometimes when we are involved in R&D and innovation project, we do not take into account the acceptance of the society. So I think that we have to overcome also social hurdles, and this is also a good point that is taken into account in Sharework project. So now we move to our brief questionnaire. So here you have the question, what would negatively impact job satisfaction of the worker adopting the technology? Working environment, social pressure, mandatory use of technology, and all are correct. So you have 1 minute to answer this question, and we have already the 30% of the attendees that replied. And you, Alexandra, you have also a few questions already in the question tab.
Oh, good.
The next session. Okay, the 62% of the audience replied already, and the main answer has been
the good answer. Yeah.
Okay, so if you want
that's good. That's good. So yeah, I wanted. Sorry, I have trouble finding the window. Okay, so I see the survey now. So all are correct, and all are based on the fact that the pressure can come from anywhere in the work environment, and that understanding work environments allows us to identify all those pressure and address them and to keep the job satisfaction good and improve it, because that's ultimately the goal of the collaborative robots.
Mm-hmm. Yeah. Okay. Thanks a lot, Alexandra, again. And now we have our quick survey. Not more than 30 seconds. And then we will have our last talk. And there is no need to introduce him again. It will be given by Dionysis Andonas again. Okay, so the service is already finalized and we can move to your presentation, Dionysis. That will deal with the towards seamless human-robot multimodal interaction, and which is the approach that is taken in Sharework framework. Please, Dionysis.
Okay, thank you very much for the interaction. So this presentation now will focus mostly on what we call in Sharework module number 9, which is the development of a multimodal interaction between the human operator and the robot. We take the topic from the beginning. As mentioned even earlier, industry wants to focus productivity and flexibility for keeping up with the market requirements. In this context, human-robot collaboration is very appealing because it combines the human intelligence with the tireless repeatability of industrial robots, with the main target, of course, of increasing this flexibility and reducing the physical strain. Okay, in theory, human-robot collaboration could be characterized as perfect, but what is needed for reaching to seamless HRC? Mostly, there are two things. We have to establish an efficient interaction pipeline and also a reliable safety system. If we have both of them, we will end up with consistent key performance indicators, which will make those solutions appealing to the industry. And we will also guarantee the safety and also the sense of safety of the operators, which is important for the acceptance of the solution. Now, for this session, we focus on the interaction. The interaction is very important to be established between those human and robot colleagues in order to synchronize the actions of both agents and also promote the awareness from both sides. The awareness now can be characterized as the humans will not be by mistake interrupt robot activities, as robots' current user actions are communicated to them, and in parallel, robots will not interrupt humans as their actions will be known as well. This is important for avoiding, for example, unexpected system stops from the safety systems that guarantees the safety of the operator. The operator will not enter into inconvenient situations where feels threatened by the robot. And in parallel, we have also to state that the robot hardware is not also stressed from dynamic adaptation of the speed of emergency stops and so forth. Now, through the years, human-robot and robot-human interface is an area of growing interest of, especially in the last decade. But despite the advances in computing and hardware performance, still today there are limitations on the management of complex interactions and behaviors. So what what we are doing in Sharework, what is our target. In Sharework, LMS has worked on the design development of multimodal interaction pipeline that is used for sharing valuable information regarding the manufacturing process and also the robot actions to the operator. And in parallel, this pipeline will allow the operator to effectively interact with the robot or the system without compromising manual operation productivity, because at the end, we want the operator to be able to focus on its job and not stop it in order to manage and control a sophisticated system. This approach is summarized in this schematic here, where our module could be characterized as this interface or this pipeline that uses different modalities like visual, sounds, augmented information, gestures, voice, touch, and so forth, in order to communicate robot and system control information, and also trajectories, safety zones, and other important information we are going to see. If we put the interaction module within the whole Sharework architecture, as Simona described in the introduction of this workshop, Sharework is a modular project. It has a number of modules that address the most important aspects in the symbiotic environment. So our module number 9, the interaction module, is responsible for parsing important information from motion planning or task planning or ergonomic evaluation module, or even the safety modules, between those modules and the operator. So the module number 9 would be characterized as the Shareworks front end, and consists of a number of devices that are mostly wearable and are responsible for communicating a variety of important information. The system could be characterized by its flexibility, and I'm talking about the interaction module, because the number and type of devices that can be connected is not a limitation. And this is important because in case of failures or known issues, those devices can be replaced. If we have a closer look now to the architecture and also the information flow, the interaction module could be constructed on 3 layers. On the top layer, we have the modules broker, which is responsible for communicating through ROS with all the Sharework modules, either for human system or system-human interaction. At the intermediate layer, we have all the available end devices that host each specific application, and then each device, according to its hardware specification, supports different modalities like that serve here inside or allow voice commands, gestures, or touch. Now, if the operator wants to interact with the system, for most functionalities there are several ways, but depending on the preference of the user, if an input is given to the system by one or two of those modalities, then the related application is responsible for translating this input into valuable information, and then through the broker, it will be communicated to the rest of the Sharework system. The opposite scenario, if the system wants to interact with the user, standardized ROS messages will be communicated to the broker, and then this one will parallelly pass this information to the end devices that, according to their capabilities, will present it into augmented format or through a screen panel or any other means. Accept this kind of flexibility and the redundant way of parsing this information, another aspect of our module is how we will be able to personalize them to make them more usable and more intuitive for different types of users that have their own characteristics, their own preferences, and also their own level of experience. In Sharework, the users can edit the information environment and select the amount of content of information that's communicated, and also the end devices that they want to use. Those options, in combination with the level of distraction details, for example, or the positioning of the notification panels, or the activation or switching off modalities, consist of a number of parameters that are used for tailoring individual profiles that can be stored and retrieved upon operator registration to the system or operator login. And this is important because, as we can see in a qualitative way, the type of information, the type of modalities that is needed for the user is related to the trust and also the experience that the operator have. And by mean trust, I mean the trust to the system and the collaborative workstation, and is also related to the complexity of either the system itself or the assembly operation. So by combining those three attributes, there are different chances that specific modalities are more important than others. All those design considerations and our work in the project have led to the release of a number of prototypes of applications. Here on this indicative slide, we can see screenshots for at the left side of the first version of the augmented reality application we have used for powertrain assembly. We can see that this application is able to communicate in augmented format warnings, trajectories, ergonomics, communicate the robot status, and in parallel support operator during the assembly process through textual instructions or even holograms and physical object detection. And in parallel, similar information, but through different modalities due to the different nature of the hosted device, can be provided through a different application which is hosted on a conventional Android tablet. So similar information is provided, but this time on a screen-based application. And finally, for more experienced users that want just plain instruction about what is the current tasks and also want just a feedback button, we also have available smartwatch application that's, as we can see, keeps only the most important information for synchronizing the human and the robot agents. At this point, I think the best way to describe those applications is to see some examples. For this scenario, the operator at first calibrates the whole the augmented reality application, places the panels in a convenient way, and then logins into the system. This login is important in order to customize the application according to the operator's needs. We can see that currently the operator activates an augmented reality application, smartwatch application, and also a tablet. And when the robot activities are running, we have augmented visualization of the robot trajectories, or I will push a little bit the video, augmented visualization of the trajectories, or at the same time in 2D format through the tablet. In parallel, we have augmented information about the current assembly scenario, textual instruction, augmented items, and also we have physical object detection. So the object of interest is highlighted on the workstation. I have to say that this black window is not appearing in the operator's field of view, but this is something that we have only in the screen record mode. We have arrows on where to locate and position screws, or we have figures like a manual in the tablet. And in parallel, the operator is able to provide feedback about the completion of the task, either through gestures in the augmented reality application, either through touch, or even augmented buttons, as we are able to see here. This process is repeated and or can be changed according to the preferences of the user. Here are some indicative examples with warning about the robot movement and also identification of the robot trajectory. Here we can see also real-time ergonomic feedbacks from the ergonomic module that all described before. I will skip it a little bit. Okay, and now we may say that the operator has completed its task, and now after the end of the shift, the operator is able to navigate through the tablet application and see specific ergonomic scores or ergonomic issues that are also correlated to the active tasks. So we also give a mean of having those ergonomic results even after the runtime. Okay, here we see another demonstration which comes from a use case of Sharework. Here we use only the augmented reality application, and as we are going to see, functionalities like ergonomic feedback or textual instructions or arrows that indicate where the operator should perform a task are presented. Augmented models highlight what the operator should do and where should place the parts. In parallel, when we get to a robot task, we will be able to see a robot trajectory that highlights the path of the robot. As soon as the robot executes this trajectory, the line is erased. The operator can move the panels and store their position in the profile. And then we move on to a final indicative demonstration of the module that is used in the shared workstation. Once again, the operator logins to the system, and information from the system operator is provided through all connected interfaces. At the operator's point of view, we can see once again the robot trajectory. This time, the operator interacts with a high payload robot and is able to move around the workstation. In parallel, the safety zones, as they are monitored from the safety system, are visualized to the operator. So we prevent that the operator by mistake enters into a yellow or red area. So the required separation is achieved and the robot is able to complete its task. And then we move on to a manual guidance operation, and controls and buttons for fine-tuning this operation are available either in the tablet application or even the augmented reality application that also supports voice commands through the integrated microphones. Similar to the first cycle, now the robot picks the second door. Trajectories are also visualized in the tablet application. We have warnings, we have also audio signal that the robot is moving. So in case the operator doesn't have direct sight on the activities of the robot, the voice, the audio notifications will make sure that the operator is aware about this motion. And this is how this operation is completed. In parallel, I would like to highlight that we also integrate some conventional HMIs in this use case, like these LED strips that depend the color, highlight the status of the robot, or even this, let me find it, this LED strip here, and also an LCD screen that provides useful insights about the status of the gesture-based manual guidance system, and also the status of the driver. Okay, we may conclude now with the results and what we have learned from those achievements. For the first video and the first version of the application, we have performed a number of tests using, once again, different subjects. The results indicate that the system is flexible enough and robust, even if we plug in or remove end devices, the using wearable device present the efficiency and also great usability because users were aware about the usage of those devices through their everyday life. And an important comment is that the interaction through voice and gesture was very helpful because the operators didn't have to retrieve any buttons during their manual operators, so they could provide direct feedback or control easily the system. By providing questions based on the system usability scales on 80 subjects, we have an overall score of 78%. We also use their comments in order to improve our applications, and some of those comments include that the personalization of the system was very convenient because they could tailor the application based on their needs. The application helped them to limit errors, so we didn't experience significant errors during the assembly routines, and we ended up with high awareness. So the operators at every time knew what the robot is about to do, and they feel that the acceptance will be increased through those interfaces. At this point, I would like to say that those results could further be supported by the training applications I described earlier, because even though the module number 9 includes intuitive applications, nevertheless, it's required to introduce a user on how to use them, and this is the purpose of module 14. So that's all for me. Thank you very much, and looking forward for any kind of questions.
Thanks again, Dionysus, for this brief lecture. So now we move quickly to the questionnaire. Okay, here you have. If you customized your own interface environment, what would you prefer? All features enabled, plain instruction, detailed assembly instruction and plain robot information, detailed robot information and plain assembly instruction. I think this is another question from Dionysus to sound out a bit.
Exactly.
There
is no right or wrong answer. This is just an important feedback for our work.
And you, Dionysus, which one would you prefer?
I would start with everything to be detailed, and then as soon as I felt confident, I would, of course, limit the information that's provided as soon as I felt confident, either the interaction phase or the assembly instruction.
Okay, yes, so here you have the answers we got. Yeah, at the beginning, for sure, all the feature enabled. And then we have the detailed robot information, and in the third position, the detailed assembly instruction. So, yeah, I think that, yeah, it's an important feedback from the attendees. And now we move to the next brief survey. Again, just, yeah, 30 seconds to reply to it. And in the meanwhile, we will get prepared for our next question and answer sessions. So again, I encourage you to ask your question if you haven't done it yet. And yes, we have already a few that will be answered soon. Okay, so also this survey is finalized. So now we move to the question and answers. Also, I kindly ask you to the speakers to open the camera. We have a first question that was shared early this morning from Sharon Kaur for Paul. Great talk. Do you have any advice for doing ergonomics assessment with assistive technologies like exoskeletons? The posture is the same, so it is difficult to use a posture-based assessment. Paul?
So when talking about assistive systems like exoskeletons, I could give you the hint to use or check or make some research in general for other measurement methods, especially other human models are required to model, for example, biomechanical behavior. So you could check for anybody or OpenSim software. And there's also a partner project in the EU Horizon 2020 framework called Sophia project, where the colleagues, as far as I know, also dealt with exoskeletons. So you could also check this out. So project-sophia.eu. And in general, probably you might use techniques like electromyography and enhanced simulation software to model your ergonomics or model your ergonomics for such on-body assistance strategies like exoskeletons.
Okay, thanks a lot, Paul. I think you have also shared your email in the case they want to get in touch or they want some more detail about it. Then there is, a more general question. So has anyone done any work on cognitive collaboration and not just physical, like decision making? This was addressed to Alexandra, but I think that can be somehow answered by all of you.
Well, as far as I am concerned, I haven't. In Strain, we have an expert in cognitive science. So if you contact me, I can ask her the question, like transfer the question. So we had, like, for Sharework project, we have her working at the beginning of the project, so giving cognitive science perspective on the project. And then I came along and had a more social and political point of view. So it's a bit, I'm not an expert on that, so I can't really say I did that.
Thanks, Alexandra. You have also other two questions from Janina Ferreira. The first one, did you use Likert scale on the usability questionnaire?
I think, yeah. So that's another point. I haven't myself done the usability questionnaire. One of my colleagues did that. And from what I know, yeah, we use something like that. Like we adapted the system usability scale and followed like a standard method to do that. So I think if it's that you're talking about.
Yeah, and also Janina is asking, I mean, she said that the work is really interesting. And if you have any paper published about your work.
So I don't think on the Sharework project, I don't think we published any research paper. However, we published 2 deliverables that are open to the public. They are in the references I gave to Marina and so on. So you can find them on the Sharework website. And otherwise, we have cognitive science research, but as I said, one of my colleagues is doing that. So if you just send me a mail, I can put you in touch with her on this topic.
Thanks again. And then I have a few questions for Dionysis, a bit more general. The first one is which are the benefits of using augmented reality in the training of operator. And the second one would be more related to wearables. Do you have any limitation regarding the batteries and so on?
Okay, we'll start with the part with the augmented reality. The benefit is that we can overlay digital items in the physical world. Of course, the experience from walking around the real workstation when the experience of having walking around a virtual workstation is not the same. Moreover, the cognitive workload when using the application is less because, as mentioned, the augmented items are those that really matter when we have this kind of application. So the digital information is limited, and now if I go to the second part of the question about the limitation of the wearables, yes, this is a problem. However, in Sharework, we have worked on it through the described architecture of the Module 9 interfaces. And as soon as if the application is plugged into the system or removed due to a failure or battery limitations, then the remaining application can support the required functionalities. And also the fact that we use devices that are commercially available in our everyday life makes this integration more easy. In a few words, this would be my response to those comments or concerns.
Yeah, this is, the most common concern that also arose, when we got a few European Commission feedbacks and so on. And now we got also a new question from Tanel Aruvali. Was there in the project anything implemented that supports specifically resilience in human-robot collaboration?
Maybe it depends when we are talking about resilience and the domain of the factory or planning or flexibility of our resources. Yes, therefore we have our flexible modules, which can be part to achieve resilience in context of productivity, resilience in the sense of human cognitive resilience. So I don't know how to declare it exactly, was not, I think, in the focus of the project.
I would also add here that within our project, our modules have been integrated and tested as well with high payload robots or collaborative robots. At the same time, we use human-centric design in the modules, and at least for the modules we described today, we also show that we have available a number of customization options to make them more personalized. So we also have resilience in aspect of human factors, not just the technology implementation. Personally, would add also this.
Okay, so I think we haven't any other questions from the attendees. So thanks again to the speaker for this nice presentation and training courses related to the human factor that are intervening in human-robot collaboration. And so now we have just our last slide. Yeah, so we would like to invite all of you to our next training activity that will be the 8th of June from 2 to 5. And it will be dedicated to human safety and cybersecurity approaches in human-robot collaboration. So the registration is already open, so I hope to see you all there. And on the other side, I would like to remind you that you will get the recorded session, so you will be able to get more details in the case you lost a few of them. And you will also get a survey in order to provide your opinion on the quality of the training session, and it would be really, really nice to get your opinion or suggestion on that. So thanks a lot for coming, and thanks again to the speakers. I hope to see you again soon, and now it's time to close the session.